reminder of what garbled circuits are, and I'm going to do it already in this formalization, which is used in the paper. And I'll try to make it as intuitive as possible. So please, if you've got any questions, just ask. Also, perhaps this part where I am talking about garbled circuits, this is the most important part of the talk. I mean, after I'll cover this, how it works normally, the additional tricks will be possible to explain like from the high level, but this thing is slightly technical. So what's the idea? We've got a circuit, sorry. For example, like this. It's a Boolean circuit, and we want to evaluate it with inputs from two parties. With inputs from two parties in such a way that the parties does not learn each other inputs and they only learn the output, nothing more. So the parties are traditionally called garbler and evaluator, for the reasons that will be explained just in a minute. The protocol it's not symmetric. I mean, the garbler and evaluators have different roles in the protocol. Roughly speaking, the garbler will prepare the circuit in a very special way, and evaluator, as the name suggests, will evaluate such prepared circuit and send the output to the garbler. So, how does the preparation goes? So the garbler picks a random mask lambda for each of the wires, so each of the arrows in the circuit. And the idea here is that the evaluator, while evaluating, will never know what value is actually on the wire. He will know only the masked value, so the value XORed with this lambda I, the bit mask. And the other thing that garbler creates are, it's called labels here. So L0, L1, which are strings of the length kappa, which is a security parameter. And they are basically encryption keys. They will be used as encryption keys. So the idea will be that the evaluator, while evaluating a given gate, will learn the masked output of this gate and an encryption key, which will allow him to proceed with evaluating the next gate. This is on the next slide, actually. So, so let's spend maybe a bit more time on this slide as much more is going on here. So the garbler for each of the gates creates what is called a garbled table. So let's now investigate what's the truth table. This thing is never shared, the truth table. It's just for the sake of explanation. So basically on each of, let's focus on this AND gate perhaps. So it's got two wires which are incoming. And there are associated X dashed and Y dashed are the associated masked values. So let's say we are somewhere in the middle of evaluation of the circuit, or evaluator is in the middle of evaluation. So he already knows the XY, X dash and Y dash, which are the values for these two wires. So say he knows that it's 0 and 1. Additionally, evaluator knows L0 for this wire and L1 for this wire. These are associated labels or decryption keys. So, so he knows that he will be interested in this row, and he will be able to decrypt this thing, the z dash with the next L label. And where is this hash thing, the hash function? Well, it was misleading for me initially, but this basically is just for the sake of encryption. I mean, this is the trivial encryption by XORing with some hash. And to actually, I mean, to decrypt, you of course need to XOR it with the same hash again. And to know this hash, the evaluator needs to know two labels corresponding to these masked values. Well, gamma is just the label of the wire, so this is known, and 0, 1 is are the values of the masked inputs. So if evaluator is somewhere in the middle of the evaluation and knows appropriate masked values for two wires and their corresponding labels, he is able to compute the hash, hence decrypt what's this row in the garbled table, and recover z dash 0, 1 L and corresponding L. So what's z dash 0, 1? Well, that's a masked value for the output of this wire. So this in turn will be used for the next gate. So after decrypting this row in this garbled table, evaluator knows the masked value for this wire and knows what's the label for this value and this wire. So then he can do basically the same thing for the next gate, and so on until he gets the actual output of the whole circuit. So this is how it goes where if we're in the middle of the thing. So now the question is how to actually start it. I mean, how to get to the first gate. So additionally to all of that, Garbler needs to send its masked inputs and corresponding label to the first wires. So this is just for the sake of starting this process. And the last thing is that some of the inputs are evaluator's inputs. So here evaluator is B. Actually, two of the inputs are his. So he knows what's the value here, although he does not know what's the label, which will be needed to decrypt a given row. So this is done. He recovers the label as in normal garbage circuits by means of OT. So the Garbler creates two labels, and the evaluator takes the one which is corresponding to his input, and the Garbler does not know which label was taken. So this is perhaps the most crucial part of this talk. I mean, if someone wants to take home just one thing, it would be nice if that would be this thing, because we'll be building on top of that. So if there are any questions, I'll be happy to answer.
I have a question.
Mm-hmm.
So I'm just trying to understand how the graphic and the table, how to match together. Okay, so if I understand correctly, the x hat and y hat, is that the lambda I in graphic? Or
no. The x hat and y hat is the actual value on this wire XORed with the lambda, with the mask.
Okay.
So actually, investigating what's going on in this truth table may be illuminating. So this is a pretty tricky, tricky way to write the truth table, but it's going to be useful we'll see in a few slides why we write it like that. So if both of the masked values are 0, then how to compute the masked output value? This is for the AND gate. So what we do is we take AND of two masks here and XOR it with the mask for the output drop wire. And if one of the values is 1, we just flip one of the masks. So actually, we could XOR it with 1, but well, like it's the same as just negating it. So yeah, I hope that it answers the question. Is my cursor visible, by the way?
Yeah.
Okay.
Yeah, I think it's good now for me. Yeah.
Okay. So now, after this thing is prepared, the evaluator, gets the tables for each of the gates in the whole circuit. So now the evaluator is able to actually evaluate it in this garbled form. So what happens after computing all the gates is that he gets, in this case, output is a single bit. So he gets this 1 bit of output, which is not output of the actual circuit. It's output of the garbled circuit. So it's XORed many times with different masks in the process. So at this point, evaluator knows some value, but it's meaningless for him just yet. So what happens later is that evaluator sends this masked output to the garbler, and the garbler is actually the party which can make sense out of it. I mean, he knows all the masks, so he knows how to perform this XORs again to recover the true output. And then after recovering it, he either sends it to the evaluator, so they both know output, or not, depending on the use case, probably. So that's the basic idea, and there are some problems with that. Namely, problem 1 is that they need to trust each other on many steps. In particular, on these 2 last steps. I mean, evaluator in theory could just send anything, and the garbler also could just lie. So it could happen. The biggest problem is that it could happen that garbler got the correct thing from the evaluator. So garbler would learn the correct output, but then he would lie to evaluator about the output. This step 6 is the one of the most crucial. And the second problem, which is perhaps even bigger, is that garbler can try to learn evaluators' inputs. So how could that happen? So garbler could create this table in a way that in some of the rows there are some reasonable values, but one of the rows is totally corrupted. So then the evaluator will notice this corruption only in case of having some very specific input. So, and then after learning that this row is corrupted, well, he would have to abort. So from the fact that evaluator aborts, garbler would learn something about the evaluator's input. This argument is a bit tricky because, well, one may ask, so why does the evaluator have to abort? Why can't he just pretend that everything is okay and send some random thing as the output of the circuit to the garbler? So this was not touched in the paper, but my answer would be, and I think it's correct, I'm not sure, is that the garbler can prepare the circuit in such a way that only some very specific subset of all the bit strings are possible outputs. So then if the only idea of evaluator to send something to Garbler is to guess the output, there are big chances that he will guess something which is not even a possible output. So, well, he would still have some chance to cheating the Garbler when it comes to concealing the fact of aborting the protocol, but with some probability, Garbler would learn that he actually aborted and not performed the protocol to the end. Is this problem clear?
Yeah. We'll see.
We'll see. Okay. So the second problem is a bit simpler to solve. The first one is a bit more tricky. So we're gonna work on making this garbage table better, but also more complex. So well, sorry for that. So this is the garbage table from the last slide. So the idea now is that we do not want Garbler to know the masks. We actually do not want anyone to know the masks. We want to have masks shared among both of the parties. So this is the shared garbled table. So instead of the actual output, we have the output shared between two parties. So how will it work now is that there will be some additional protocol after which the parties will end up having shares of the garbled table. Then PA will add its own parts and send its share to the evaluator. Okay, so how does it solve privacy matter? So right now, as the Garbler does not know the masks, he still can corrupt one of the rows, but he does not know to what inputs this row corresponds, as he does not know the bit masks which are applied. Hence, even if he does corrupt a given row, there will be some chance that the evaluator will have to abort, but it will not give any information to the Garbler because he will not know the specific conditions in which the abort happens. So this is slightly informal. To actually formalize it, we would need to be after this simulation part, which we are kind of heading towards, I guess. And this is not by far not the final stage of this protocol. So I'm not gonna explain it all that much. We want to make it even better because this part would still have a problem. So the problem is that these R's, I mean, they are not committed anywhere. So the Garbler could just flip one of the R's and make the output wrong. And it could happen in the way that, well, the whole protocol would proceed as normally, with the exception that on the one of the gates, Garbler flipped all of his shares. So the actual output would be the negative of the output, which is created from this protocol, and this information would be known only to Garbler. So that's a heavy violation of correctness in a way where Garbler would learn the final output and evaluator would not. So we want to prohibit that as well. And how to do it? Well, we want message authentication codes on the errors. So now the next table is coming, and it's gonna be even bigger. But I'll try to explain what each part is responsible for. So the last garbled table looks like this, and this is the final form of a garbled table. We're not gonna make it even more complex. Or perhaps I should. Maybe that's sorry. First, the next slide. So first, what kind of message authentication codes are we going to use? So if PA holds some value, then we want PA to hold also message authentication code for this particular value. And in this scenario, we want it to be in the form of some one-time key, K, and some global key known to be delta B. Both of these keys are known only to be. But this one is global in the sense that it's going to be the same for every authenticated value known by PA. And this is local in the sense that PB will create this key each time the new value will have to be authenticated. So this kind of marks are additive. That's well, pretty obvious consequence of how they are created. And they have, it may look that they have a pretty complex form, but we're gonna see that this is just to prepare for a trick which will allow us to make some computation local instead of having it global. So the only thing we need to remember, okay, the thing we need to remember about this keys is that KX and delta B are known to the other party. So the first party knows the value and M of this value.
Can I ask a question?
Sure.
So what is addition here in this slide?
What's the addition here in this slide? That's a great question. So where does this max live? It's XOR, actually, I think. I mean, that's the only obvious addition. Sorry for using this. I'll look at the paper, but I'm pretty sure it's XOR. Yeah, sure. It's XORing. Sorry for using the wrong symbol.
So then if you use K of X or delta of X, then what does it really mean?
If I use K of X XOR delta of X, I don't understand the question.
Oh, okay. The question is what is K? And yeah, what is K?
K of X is not K times X. It could be a lower script. I mean, this whole thing is a one-time key, and it belongs to the same space everything belongs, which is the sequences of length kappa.
So it's just some okay. And lambda of X.
So lambda is also the sequence, and lambda of X. What's lambda of X? Actually, I didn't ask this question to myself before, but we need some kind of multiplication here. Oh, okay, because X is a bit here. So X is a bit, which means that depending on whether it's 0 or 1, we either add lambda or not. Sorry for confusion. So, well, I'm in the PDF. I can't write here, but yeah, X is just 1 bit, and we want to authenticate 1 bit. So the message authentication key is either the one-time key or the one-time key plus the global key, depending on whether X is 0 or 1.
So this would mean that this is a multiplication, X times delta key. Yeah. Okay. Okay. Thanks.
Yeah, sorry for the confusion. Somehow assumed that it's obvious, and it's not. Okay, so we have this max where first party which knows the value knows the MAC of this value, and the other party knows both of the keys. So now we can see it's gonna be further explained over the next slides, but now just to compare it to the previous version, we do basically the same and just add the message authentication key to the R and the local key here to the same R, of course. So now let's go through this table row by row. So these things are beaver parts of the beaver triples actually. So what do you want from it is that we want R00 plus S00 to equal Z00, which is output of this particular gate. And sorry for the dashed being displaced. So what's the output of this particular gate? It's this is the AND gate again. So this is X AJ and Y AJ. So to have these values, we need to run some separate protocol on the side and it can be done before this will be pushed to the preprocessing.
Do you when you run the beaver triples generation, do you know what ZIJ is beforehand, or is it going to be random? A random value?
I run for every. I mean, I run it for 0, 0, 0, 1, 1, 0, and 1, 1.
Okay, so we know the values for that.
So yes, this works with masked values, but here we know that. I mean, this is the row for 0, 0, for example.
Okay.
And we know what's the output of. So now here we have message authentication keys for ours. This is just basically encryption. I mean, we are using hash, and this is the same as in basically the same as in normal circuits. And now there is this thing. I mean, okay, we've been talking about beaver triples, so I hope that it's more or less understood that we are splitting the masked values in a way that they are kind of multiplicative. But now we have this split labels here, and we didn't talk anything about the split labels. And the reason is why we didn't talk about it before is that we're going to use some tricks, so we do not actually need to care about it, and we do not actually need to make any specific preprocessing to have them shared. So what's the deal with this things? So PA, meaning the garbler, knows all the labels because he still creates the circuit, and he still creates the label for each potential output of each given gate. But what he doesn't know, and he cannot learn during the protocol, is Z00, which is the output of a gate. So he cannot know the L with 0, 0, Z00 in the lower index. I mean, if he would knew what label should be in this row, he could basically evaluate the circuit on his own. So what we want now is we want this label to be shared and during evaluation recovered only by the evaluator. And now there's trick. And this trick is technical, but what's worth remember perhaps here is that this can be actually done locally. So we did a lot of preparation to like this message authentication codes are in this form. They could be simpler, but they are in this form where there are two keys. And also what we do, before we did not talk about any particular constraints on the labels. So basically they could be totally independent decryption keys. So right now we do want to have a constraint. So we do want to have a constraint that one of the labels is the other one XORed with delta A, which is this global key for the garbler. And then after some derivations, we can see that actually this label, which has an index which is not known to the garbler, can be represented as XOR of two things. And the cleverness of it is that the first of these things is known to PA because, well, this is the label for 0, which is known to PA. This is the R00, which is PA's share, which is obviously known to PA. This is his global key, which is of course known to him. And this thing is the part of the authentication of S00, which is known as long as we do actually have authentication codes for S00. So if we do have a proper authentication pattern, this thing can be computed locally by PA. And what's this thing? Well, at first it may look a bit tricky because it also has this key S00, which should not be known by PB. But in total, this is just the MAC for S00. So if we authenticate also S00, then this thing can be locally computed by PB, and this thing can be locally computed by PA. So we kind of do not need to care about this shared labels during the preprocessing. Okay, so what do we need to care about? What we need to care about is how to create beaver triples in a way where we are able to provide max for both R and S, because both are necessary. Although not both of them are in this table, we do need to authenticate S as well, just for the sake of splitting these labels. So we want to have a beaver triple which has both of the shares authenticated. And I know that it looks like a cliffhanger. Unfortunately, I'm not gonna give a detailed answer how to do it. The first idea is to use a semi-trusted server, of course. I mean, this is basically preprocessing, which is independent not only from the inputs, but also from the circuit. So we could just get from someone we trust a lot of such triples, and well, they could last us for life. So why it's semi-trusted? Well, because the server has no chances to learn anything about the protocol. I mean, he can just lie to us for the sake of trolling, probably. But if he doesn't do that, then we're good. And the other idea is the cuts and choose I mentioned at the beginning, which is the chapter we actually missed, unfortunately. And the very rough idea of this cut and choose is to generate a lot of triples in using the protocol which assumes honesty of both of parties, and then check and reveal and check big part of them and use only the remaining ones. So with that, we get some probability that the remaining ones are okay. And then, as I understand, I didn't read it very thoroughly. As I understand, there are additional tricks which work under the assumption that majority of the triplets are okay. So there are tricks to make all of them okay. Well, I would be really happy to see that thing eventually. What's interesting in this paper also are the test results. I mean, they did a proper testing, and I think this is a good opportunity to talk about how effective MPC protocols are in general. So, like, this is the paper from 2017. So, well, I didn't do a super comparison for all the other protocols, but one of the main selling points of the paper is that they improve over the previous results when it comes to two-party computation. So I think that seeing these results should give a pretty good intuition on the state of the art, basically, when it comes to effectiveness. So there are two different tests. First one is with three functions: hamming distance, integer multiplication, and sorting. And looking at how it goes with the network, basically they are not super heavy tasks. I mean, one of them is, for example, sorting 4,000 numbers. So it takes 72 seconds. Seems quite a lot. The vast majority of it is a pre-processing. So in the actual implementations, they do have two pre-processing phases: the function independent pre-processing and function dependent input independent. And this is basically just a formal trick for the proofs to pass. They write that actually both of these pre-processing are about basically generating these triples, although it's significantly easier to prove safety when some of these triples are generated after the circuit is already known. So, well, this independent and dependent, basically they are both pre-processing. So the vast majority, like 70 seconds from the 72, are spent on pre-processing, and only 2 seconds are online on actual evaluation. But still, like these times, they are not super optimistic. And bear in mind that this is a two-party protocol which does not easily generalize to more parties. So these ideas here, they do not have natural generalization for n-party protocol just yet. And there is another test, which is also a comparison to the previous work. And this is the evaluation of symmetric encryption in the amortized setting, where multiple encryptions are evaluated at once. So, well, we can see some improvement here, although apparently the more encryptions are evaluated at a given time, the less improvement over the previous work it gives. So that's all for I prepared for today. I know that was pretty technical. I think the part which I find the most interesting here are the actual results, because I don't know, for me, these are the ones which gives the most intuitions on where we're at with MPC. Like what's possible, what's probably not possible yet. And the answer is rather pessimistic. I mean, everything, like these computations which are not unreasonably big, they take, like, this is a prohibitively long time for like blockchain applications or something like that, I think. So with this pessimistic notion, that's all.
Thanks. That was a good presentation. It's surprising that it takes 72 seconds, I think, for
I mean,
sorting.
Yeah, it's surprising that everything takes so long, generally, for me. I mean, I was definitely expecting lower numbers, and this basically means that, the question I asked myself recently is, how does it compare? I mean, Ethereum is also not like a very optimal computational paradigm. So if you want to make some computation on Ethereum, you are also very much computationally bounded. So interesting question for me would be, how does it compare? I mean, if you would have like this off-chain MPC, is it faster, slower than Ethereum? I mean, how much slower? How much faster? I don't know it just yet, although that would definitely be interesting to check. And
so I think saying Ethereum is slow is not necessarily correct, because so Ethereum is just like one thread computed by many people at the same time. So it's not necessarily slow. It is just that there is this overhead of like hundreds, thousands, or even millions of nodes computing the same thing. But all of them computed rather quickly, I think.
yeah, I'm not saying about like that Ethereum is theoretically slow, and what I was saying is that in practice, like there is a gas limit for each block. So there is a very practical bound on the number of computations which can be done in a given unit of time. So this could give a base for comparison. And I think this comparison would differ a lot depending on the type of computation. For example, things like hashing are pretty fast on Ethereum, and takes they have terribly big circuits which are corresponding to them, so they would be rather slow on MPC. Not sure how about these things, like for example, sorting 4,000 numbers on Ethereum.
How do you, so if I understand correctly, you were planning to use MPC with blockchain or something?
I mean, that's why we are learning is that we want to eventually deploy some version of it. But still, we don't have a full intuition even what's possible, what's not. And this is a good question to start. Like, if you would deploy the general MPC with results comparable to the current state of the art, like how useful would that be? Comparing, I mean, how expensive the computation would be? Would it be as Ethereum, or 100 times more expensive and slow, or maybe less? Still hard to say for me.
Yeah, it's hard to know like what the state of the art is, I think.
Yeah, I mean, this, I think, for example, I've seen somewhere like the symmetric encryption. Basically, I think it runs in the similar time as computing the hash function, roughly. And the hash functions are actually, they do have kind of not constant gas cost, but depending on the string length. So, for example, such things could be compared, like roughly.
not sure this would be a fair comparison. I think what you might compare to computing a hash function over MPC is like the cost of the prover to construct a proof for a snark, which then is submitted to Ethereum. Like this would be maybe a fair comparison, but so a hash function is just a built-in in the virtual machine. So
yeah, it is. I mean, in this comparison, like that's the worst comparison for MPC because Ethereum is particularly good at it, and well, MPC is not.
But there is nothing private, or there is nothing multi-party computation like in Ethereum's hash function. So then this is like a single party computation on Ethereum. Then
okay. So my idea would be, let's say you would like to make the whole Ethereum private. Okay, like everything what runs on Ethereum right now, you want it to run on MPC. So would it be how much lower would it be? Assuming that you've got 2 nodes. I mean, let's say we have this blockchain with 2 nodes running this particular protocol. I know that it's still not like a formally correctly stated question.
It's an interesting question. Huh?
Yeah, and I think it's.
But so, how would it run? You know, who are the parties?
I don't know. Like there are 2 trusted guys, like the most trusted guys in the world. They are running the blockchain. It doesn't matter. Like, of course, if the answer is like optimistic and the answer would be, yeah, it's pretty fast, then you can start designing how actually should it run. But if the answer will be that even with 2 nodes, it's, I don't know, 1,000,000 times slower than Ethereum, then, well, that's too early for MPC in blockchain. That's
yeah. So we would probably need to assume that the parties are known somehow, or we have to assign parties that permission, or a set of parties, and
yeah,
they do something, compute.
But that's not the part of the question I wanted to focus on. Like, assuming that we figured out how to kind of split all the inputs and how to make this architecture, what would we like? What would be the properties of the system we designed? And that would not be like linearly comparable for the reasons that there are some things which are very easy on Ethereum, like computing hash functions, and particularly hard on using the Boolean circuits paradigm. And there are probably computations where the difference is not that big. I'd assume that this kind of computation, like Hamming distance or something, that should be like here MPC shouldn't be that much worse as in the case of hash functions, but that's just a wild guess.
I guess they want to make smart contracts privacy preserving. So if the nodes are known or the computing parties are known, you could run it on them. I mean, yeah, I guess the question is how is it fast enough? It's what you're saying.
Yeah, but
with these techniques, would be maybe we can do run some comparisons at some point, or maybe just do a comparative comparing lots of these systems.
Yeah, I think there are papers which are aiming specifically. I mean, there should be papers aiming specifically at this goal.
And how much memory does it take, the computation? Is it would it be is it usually linear to the runtime, or is
That's a good question, but I think it's not a bottleneck here. I mean, like the question is how big the circuits need to be. Not sure either. But I don't think that the memory is the biggest bottleneck here. Time is. Anyway, I think we can conclude for today, perhaps, and see how the asynchronous organization goes for the future of the seminar.